On Friday we talked briefly about this idea, the effect of noise on parameter estimates, and then we also kind of looked at this concept of variability in predictions. We talked about the bias variance trade-off and all of this, and I did a brief demo on Friday, and then I'll do another demo today using R to kind of illustrate some of these things. One thing in this class in 102B is there's a lot more math than there was in 102A, but then the hope is with kind of your programming fundamentals, you can go from the math to something in code, and then by exploring something in code, maybe it can give you a little bit more understanding here. Okay, so we talked about how the amount of noise on these parameters will change kind of the variability here. Okay, so I think, let me see if I can pull up that code from Friday. If this works. So noise on parameter estimates, this is what we illustrated. Oh, I guess it shows up like that. Let's run this. Okay. So we said, so here I'm going to first put just a tiny bit of noise. Okay, so we're going to say the standard deviation value on my error term is going to be 0.05. Okay, and we're going to generate. This is the true model. Let me see, how can I? So in this corner down here, this is the true relationship between x and y. I have generated some random noise. I'm going to generate some random noise using R norm and a standard deviation of 0.05. And we will plot these points in gray. Okay, so we can see them vary here. And then based on these random points, we fit a model of best fit. Okay, and this is what we get. And we said, okay, let's try this a whole bunch of times. And so I'll try this 20 different times, and these are all kind of the different points that we can get, and these are the different estimated fitted lines that we have. And I said, okay, well, what if I wanted to do this 2,000 times rather than 20 times? And we can do that. And we can kind of plot PCB. We can plot how kind of the coefficient of our things compared to our variance covariance matrix. These we can see how the intercept and the slope vary. So again, the idea here is, if I continually just take random amounts of error applied to our 20 randomly selected points and I refit a different linear model, how much do the estimates of our slope and intercept vary? And we can create a contour plot of the relationship between the kind of the density of the different of this, and we will get a contour plot. Okay, and we can see with the amount of variation to be 0.05, sigma squared being that, we get a very small contour centered around -2 and 3, which makes sense because the true parameter relationship is an intercept of -2 and a slope of 3. Okay, and we can see just if I crank up the amount of variation to be something bigger, Okay, and I'll just repeat this. So all I'm doing is just using a larger s squared value. I'm going to generate new random errors, and then for each time I'm going to refit a model and see how the slope and the intercept. And so in this case, if I plot it, just kind of something happened. Oops, I guess I did it 2,000 times rather than 20 times. But we can see just kind of all the different best fit lines here compared to the original. It doesn't show, but so we can just repeat this and see and create our density plot. And if so we can see the amount of variation increases, right? And so basically the summary at the end of this section, the effect of noise on parameter estimates was that larger noise creates more uncertainty in our parameter estimates. And this is kind of indicated in this covariance term, the variance-covariance matrix of our estimated values W hat. So W hat would be kind of the vector of parameter estimates, the vector of your slope and your intercept. And then if you say, what is the variance of W hat, or of the intercept, what's the variance of the slope, you get a sense of how much variance exists in there. And this is, so the covariance is equal to sigma squared times x transpose x inverse, okay? And I said this is the inverse of the Hessian matrix of second derivatives, okay? Which it says equation 238 is how we got this. What is the Hessian? The Hessian is the analogy, vector analog to the second derivative. The gradient is the vector analog of the first derivative. The Hessian matrix is the vector analog or matrix analog of the second derivative. Okay, so think of a single curve. Maybe it's worth illustrating this out just for a quick picture. So if you think of the curvature of a function, if a function is very smooth and does not have much curvature, so just think of kind of this like smooth rolling hills, is the second derivative large or small? Okay, so let me just draw this, right? Nope, that's not the button I wanted to push. Okay, so you've got this, right? So you've got some kind of function like this, and the first derivative is the slope, right? You've got how much, these are like supposed to be tangent lines at each of these points. And the second derivative, so the f prime is the slope, and the f double prime, the second derivative, is kind of how quickly does the slope change, right? So if it changes very slowly, then the second derivative is going to be small. Okay. On the other hand, if you have something like this, where the slope goes from very steep, so very high vertical, to very high positive to very negative value, then the slope changes quickly. So that means kind of f double prime is a big value. Okay. So that's for one dimension, and you can just imagine something similar holding up over 2 dimensions or in multiple dimensions. And so the second derivative, or now the Hessian, is a measure of the curvature. Okay. An interesting thing is that, well, I don't know if this is interesting. So your loss function might return a scalar. And then the loss with respect to a vector, this will be a vector, right? A vector of the same length as w. And then if you take the second derivative, so w transpose, then you're going to get a matrix. Because basically, here you've got, let's say you've got 3 components in your, this was not intended for you guys to copy down, that's why it's all so sloppy and all over the place. So if w, there's 3 pieces in w, when you take the gradient of L with respect to w, you're going to have 3 pieces in your gradient, right? And then basically, the derivative of this is going to be, you take a gradient with respect to this, and you're going to get 3 elements. You take the gradient with respect to this, and you get 3 elements. And you take gradient with respect to this, and you get 3 elements. So you're going to have 9 elements in this, in the Hessian matrix. Okay, it's going to be 3 by 3. All right, so this is, sorry, this whole slide's a mess. I see you guys diligently taking notes, and that wasn't my intention. So, okay, so anyway, this is kind of what we call this. Our matrix is the inverse of something called the Fisher information matrix. The Fisher information matrix is computed as the expected value of the matrix of second derivatives of the log likelihood. So anyway, you take the second derivatives and you kind of get the expected value of that thing. That gives you the Fisher information matrix, or the kind of the expected value of your Hessian. And again, so the idea is, if that thing is very big, meaning you've got this kind of a lot of curvature, you have a kind of this very steep region, that means you have a lot of information. So if we think about, where did my plots go? Oh, too much. Okay, so if we look at this picture, you can think of, you have this, surface, and then you've got this one hill that's just very steep, okay? This picture reveals that the Fisher information matrix is going to be quite large because the Hessian matrix is big, and this means the data provides a lot of information about the parameters, the slope and the intercept, which makes sense because there's not much variance about the slope and parameters. So we have a pretty good idea of what our slope and intercept should be, all right? And so, on the other hand, the other picture, all right, okay, here we are. There's less certainty in our parameter estimates, and so we have less information in here, okay? And so that's kind of what the Fisher information matrix tells us. And so there's an inverse relationship between variance and information. If you have high variance, you have less information, and if you have low variance, you're going to have more information. And that's what all of this says. Okay. What if we want to talk about making predictions now. Okay, so rather than just talking about the variance in the parameter estimates ourselves, we can talk about making predictions. All right, so in the textbook, we have T nu is equal to W hat transpose times X nu. Basically, X nu is, in this case, is a vector. So if you have a linear model, your X nu is going to be the vector 1 plus the X value, right? Because in a linear model, you have your X matrix is a column of 1s plus X values. So if you want to say, I want to, in this case, we're making predictions based on years, and we want to make a prediction for the year 1980, my X nu would be the vector 1 comma 1980. Okay? W hat are your estimates of the slope and intercept, and then T nu would be the prediction that you get when you multiply those two together. The nice thing about working in vector notation is that if we had a polynomial thing or a multiple linear regression thing, X nu is still the same. It's just going to be have more terms in it. So it might be a vector of 6 terms, and W hat will be a vector of 6 terms, but you multiply those two together, and you're going to get back a scalar, which is the prediction that we're going to have. So we might want to say, okay, what is the expectation of our predictions, right? How, you know, and what is the variance associated with our prediction? So this is kind of what this chapter section is called the variability in predictions, and we want to know what is the expected value. Okay, the expected value of, so this location here, the expected value of your prediction T, the predicted value of T nu is going to be W transpose X nu, okay? Because earlier we established that the parameter estimates W hat are unbiased estimates of the true relationship W. Okay, so which we can also kind of establish here, and we see here, we said, you know, here we established that the true intercept is -2 and the true slope is 3, and it sure looks like if I took the mean of all of my different parameter estimates, I would get a mean of -2 and 3. Okay, and so this picture shows that our estimates are unbiased. Of course, on any given set of random points, we might be too high or too low, but overall in the long run, they are unbiased. And so our predictions in the long run are also unbiased. But what is the variation, okay? Well, I could rewrite all of this on a notepad and you would copy furiously. I'm going to just say, in your own time, you can kind of look through this. And if you're like me, a lot of times when I see a block of math in the textbook, my brain just checks out and skips to the end and says, all right, I hope this worked out. I don't know, maybe some of you guys take a more thorough approach. You know, I know you guys don't have a ton of free time, so probably it's not as critical. If you do want to, and you don't want to actually like have to do the derivations yourself, one thing I often like to do, especially with matrix things, is I just like to check out the dimensions and just make sure all the dimensions line up. And I think that helps me understand. And it's so important when you deal with matrices and vectors that the dimensions do line up when you do the multiplication, because that's kind of how everything holds together. But anyway, thankfully, our textbook did the math for us, and it says, ah yes, indeed, when we, our new prediction will be just our x values multiplied by the predictions W hat, and then the variance of sigma squared is equal to sigma squared. So sigma squared is the error, the amount of noise in our generated model, right? because in our generative model, we say there is a true relationship between x and t, except there's noise. And sigma squared is that amount of noise. This is the new value that we are inserting. And then this is x transpose x from the entire data set, inverse times x new. Okay, so this is like, so this is kind of an indication of how much noise we would have here. Okay, and this whole thing about big X transpose X, we will see how this plays out. Okay, so it doesn't actually take into account the what we notice is that our predictions don't depend on the actual prediction or the W hat. It just ends up depending on kind of the X values in our data. And what we will see is that in areas where there are few X values collected, this thing gets quite large. Okay, the X transpose X inverse, when we multiply it by a new X, those things will get quite big. Okay, and so here I will run through an example in R showing this variability in predictions, and this code has been posted, and I'll try to do my best in explaining what is happening in this code here. Okay, so the true model has a cubic relationship between y and x. Y is 5 times x cubed minus x squared plus x. That's the true relationship. Let me just clear all of these plots. And I'm going to say, okay, we're going to take 100 points in our training data, and then I'm going to just generate a bunch of values between -5 and 5, and this is the true value between y and x, and I can plot this. And so this is the true relationship between y and x, and what I'm going to do is I'm going to add some random noise. Okay, and so here the variance is 300 because you can see kind of the scale on which y exists, and so I will add some noise, and if I add those points, this is what we have, right? Okay. And what I'm going to do is I'm going to remove the values between -1 and 2, and we will see kind of, this will give the model a little bit of, quote, freedom in this range. Okay, so I'm going to just remove those things, and so the ones we keep are going to be these ones in red. Okay, so these points will not be in our data set. Okay, so we might as well not have these points here, but these are just kind of illustrated to show the variation that we have. Okay, and now I'm going to create a range of new values for which we want to make predictions. Okay, so x new says I want to make basically 101 predictions for x between -5 to +5, you know, in increments of 1/10. And here, let me just let me start with I equal to 3, just so you guys can see what will happen. Because I'm going to throw this into a loop where we're going to try it with polynomials of order 1 to 2 through 8. Okay. And so first I'm going to just create two empty matrices, empty matrix X and an empty matrix X new. Okay. Here, the length of X is 71. So these are, I've got 71 values in red. Okay. And then the dimensions of X underscore new is 101 by 4. Okay. The reason why it's 4 is because we are going to fit a cubic order polynomial. So I'm going to create a column, and basically from 0 to order 3, I'm going to just raise everything to these different powers. So just so you can see what x looks like, or x new looks like, let me just show you the tail of this. Okay, so this is the tail of x new, is that here I've got a column of 1s, and then, we have the values from -5 to 4.9 all the way up to 4, and so on and so forth. This column represents x squared, and this column represents x cubed. So 5 squared is 25, 5 cubed is 125. And now I'm going to fit basically a linear model to, these are going to be my 4 predictors. A linear model to, x0, x1, x squared, and x cubed. Okay, so I could do a linear model and fit each value to this using our x. Well, in this case, it's the x matrix. Or I can just use our solution, right? X transpose x inverse x transpose y. And that will give us our best fitting W hats. So here the coefficients I have are, I have an intercept of 0.39, a first order term of 1.23, a second order term of -1.19, and a fifth order term of 4.98. Okay, so these are my coefficient estimates. Okay, and then this is from equation 2.37 in the book. This is the estimated kind of sigma squared value from our textbook. So this is, if I scroll back, let's see if it appears. So again, we're thanking the book for doing the math for us. So the estimate of sigma squared is going to be this thing, and so I just implement that right here. So my estimate of sigma squared is this, okay? And then we can ask, all right, what are the predictions and the variance of each prediction, okay? So here I have t underscore new. These are going to be, what are the predictions that I have using my estimates w underscore hat, okay? And so I can see t underscore new, and these are kind of the predictions, and I can plot that. So these are the current values and points, and this is my fitted guess. And then what I'm going to do is I'm going to take the equation that we found, or not, we didn't actually do it, we just let the book do it. We're going to take this value of sigma squared x transpose x inverse x new, and we're going to do that. Sigma squared times x transpose x times x transpose x times x. In here we're it's just a little bit slightly modified. I have to pull out the diagonal because we're dealing in a matrix here. And so this is kind of the variance associated with each of the different values here. Okay? And so to illustrate how much the variance changes is I'm going to use the arrows function to go from our current prediction t underscore new to 1 subtract off the variance all the way to t new plus the variance. Okay, and so this will show us kind of, let me just kind of, so we can see for each value we kind of have a little bit of a window showing how much variation that we have here. Okay, so we can see in this region here where there's fewer points, the amount of variance perhaps grows a little bit, okay? Maybe it's not super evident. That's okay, all right? And so I can repeat this same process, but you know, perhaps I will try it with I equal to 8. And so now I'm going to deal with polynomials of order 8. And so if I look at x underscore new, let's just look at the tail here. So 5 to the first, second, third, raised to the 4th power is 625, to the 6th power is 3000, and so on, and it climbs up, and we're trying to fit polynomials of order 8 to our data, okay? So we just, we solve for it using x transpose x, x transpose y, and so these are my coefficient estimates, and we can estimate the sigma squared values. And if I were to extract the variance, what we'll see is, so this is fit with an order of 8. We can see because with an 8th order polynomial, it's going to try to fit the data as well as it can, but here where there's no data here, we could have, you know, it's possible to have a polynomial that looks kind of like this somewhere in here, right? It's still trying to fit this data as best as it can, and because it's of order 8, it has quite a bit of wiggle room to kind of mess around here where there's hardly any data. If I stick a data point right here, then it will kind of lock down the where it goes. And we can also see that out here, because it's an 8th order polynomial, this thing can vary quite a bit, and same something out there, okay? So with a polynomial of order 8, there's a lot of wiggle room, okay? And so I can kind of just try this for all 8th order polynomials, and we can see how this runs, okay? Let's just grow this a little bit. So this is what we saw with an 8th order polynomial, and with a 7th order polynomial we still see a lot of wiggle room, but it doesn't diverge as much off towards the edges. And with the 6th order polynomial, it seems like things in the middle kind of come under control. And this is what we have for order 3. And then when I drop down to 2, it looks crazy again. It looks terrible. And the reason why is we're trying to fit a quadratic thing to all of this data, right? And so, you know, if should the quadratic fit be like this, or should it be like this? You know, you're only allowed one bend in a quadratic thing, and so what's the best way to do it? You know, is it something like, you know, I don't know. So it looks terrible there. And then if we try to fit just a linear thing, basically we're either going to fit a line like that or a line like this or something in between, right? So again, the fit looks pretty bad here. Yeah, let's see. What if let me see if I can stick back one of our values here. Go back. Let me just try to stick one value back in. at x equals 0. So at 0, I think x looks like this, and so I'm going to just tag on all the x's and a 0, and then at y, we'll tag on all the y's, but also y and a 0. Okay, so now if I, does this not go? Sorry, I don't know what did I do? Okay, let me just try this again. X is going to be combine x and 0, y will, so all I'm doing is just, I'm adding on a single value of 0, 0, so that when I plot these points, so I've got just a tiny bit of, here, let me go back. I apologize. Just keep messing around with this. Okay. So let's not work. X is this. Y is this. No, it's not. Okay. I guess even though I have one point, data point there, it's not kind of locking it down here. Which is a little bit different from what I expected. Okay. When we, what we can also do is we can create, use the multivariate normal function and plot just functions if we drew the parameters from a Gaussian with the mean of w hat and covariance of w hat. Okay, so the idea here now is we fit our data to, we fit a model to the data that we have, and that generates a w hat and a covariance of w hat. Okay, and then now what we will do is we will draw random values from a new a Gaussian distribution centered at w hat and with this covariance. Okay, so it's like saying we've got you know, we are estimating that the slope is negative 2.9 and an intercept of negative 1.8. Okay, and we will say, all right, let's draw random values centered at 1.8 with a covariance of this, or variance of this, and let's draw random slopes centered at 2.9 with a certain amount of variance. Okay, and then we can see just kind of how much fluctuation exists. And so here, I'll load up the multivariate Gaussian package, and we will just randomly select some values for x and y. And then we'll try this for polynomials of different order. Okay, and so for each one, you know, what we do is, you know, we generate a new x value, and, you know, we kind of follow everything before, and then now I'm just saying, okay, what kind of polynomials can fit this this thing here, okay? So here I've got this is the data that I have. The black dots represent the data, and we say, okay, well, what's the best fit line? And it's going to be somewhere in here, and then we say, okay, what is the kind of the covariance and the variance of this thing, and just draw other lines, random lines from that multivariate Gaussian distribution, and this is what we get. And for polynomials of order 2, we get something a little bit different, and then we can start to see as we increase the order, we get a little bit more wiggle room here, and we are able to fit some of the data a little bit better, and somehow, and if we jump all the way to polynomials of order 8, we get a lot of kind of wiggliness because it's just trying to fit just the few data points that it has as well as it possibly can, even if overall the shape looks a little bit crazy here. Okay, and so that's kind of what we are seeing. Each of these is just trying to fit and minimize the sum of squared errors here, and we are picking just kind of random Gaussian random sets of parameters from a multivariate Gaussian centered at our current estimates here. If I just did it again with a different set of x and y values, we would get something totally different. Here I have even fewer data points, and I guess, so here I only have 1, 2, 3, 4, 5, 6, and so it won't won't allow me to fit a polynomial of greater order because then the rank of the matrices collapse when you do x transpose x. But let me just see. Let me just go back. Let's just delete everything. Source this whole thing. Okay. So there we go. Just fitting different kind of polynomials here, and we can see the amount of kind of wiggliness that's allowed in this region where there's no data points varies quite a bit, where the polynomial that kind of makes the most amount of sense probably fits the best of the ones. All right, so this, again, all I did here was just take the concepts, some of these equations that the book solved for us, such as the sigma squared values, and then I just basically put them into code, which you know, is a little bit different, and we're kind of illustrating some of these things. But yeah, so basically in this course we have a lot more mathematical concepts, but then when we put them into our code and stuff, it kind of, I think we get a little bit of a picture of exactly what's happening in terms of the shape of the fits that we are getting with our model here. Okay, we'll wrap up here for today, and then we'll see you guys on Wednesday then.